Hi, OK. Well, thank you for having me. I'm going to talk to you today about a subject in Fourier analysis called decoupling. Ciprian Demeter and John Bourgain have been developing this over the last few years. I think it's a circle of really fundamental new results in Fourier analysis. And I've been reading and rereading and rereading them. And so over these 3 lectures, I'm going to try to share with you what I understand so far. OK, and maybe one takes it for granted, but the lectures are supposed to be accessible for everybody from all the parts of harmonic analysis who are here, and also to maybe if there's some number theorists here. So if anything doesn't make sense, or if you have any questions, please stop me as we go along, and we'll talk about it. OK, so here's the framework for decoupling. So I have a region omega in Euclidean space. So it's in R to the n. And this region has been cut into some smaller regions, somehow decomposed. And the smaller regions I'm going to call theta. So omega is a disjoint union of regions called theta. And this is all going on in Fourier space. So now suppose I have a function whose Fourier transform is supported in omega. So suppose that the support of my function's Fourier transform is in omega. Then I can break up this function into pieces that correspond to this decomposition in Fourier space. So my function f is decomposed as the sum over the different pieces theta of f theta, where f theta is just the part of the Fourier integral that comes from theta. So it's just the integral over theta of f hat of omega e to the 2 pi I omega x. OK. So we all know that these different pieces are orthogonal to each other because their Fourier supports are disjoint from each other. So we all know this, that FL2 is the sum on theta of f theta L2 squared to the 1/2. And decoupling is about what happens if we consider not the L2 norm, but some other LP norms. So the decoupling constant, the LP decoupling constant of this decomposition is the best constant, so that something like this holds up to this constant for LP norms, so that the LP norm of f is bounded by this constant times this. OK, so let me give you an interesting example of a region omega and a way of cutting it up into pieces theta. So so we're going to look at the parabola. The parabola lives in 2 dimensions. So here's my parabola. Parabola is omega 2 is omega 1 squared. And I'm going to look at the part of it in a unit ball. I'm going to take this parabola and cover it with rectangles. So the regions theta are going to be rectangles. So the cover looks sort of like this. So these are the regions theta. And let's say that the number of these, the number of regions theta is capital A. And so each theta is essentially a 1 over a squared by 1 over a rectangle. So the reason that the length is 1 over a is that this curve has length about 1, so it should have length 1 over a to cover it with a rectangles. And the reason that this width is 1 over a squared is that there's a bit of curvature in the parabola, and 1 over a squared is the width that I need for the rectangle to cover the parabola. And when I put these all together, my region omega, so the union of theta, is essentially the 1 over a squared neighborhood So this is an interesting example, and the decoupling theorem that Bourgain and Demeter proved is the following, which I can fit it here. So theorem, Bourgain and Demeter, if p is in the range in between 2 and 6, then the decoupling constant of this situation, which so I'll write it this way, grows very slowly. It's essentially, so for any epsilon, it grows slower than a to the epsilon. Cool. And I'm going to use this dp of a. Since this is the main example that I'm going to be talking about, dp of a means the decoupling constant for cutting a parabola into a rectangles. OK. What is the small epsilon? Thanks. Yeah, the subscript means that there's an implicit constant here that depends on epsilon. So this is an abbreviation for less than or equal to constant depending on epsilon, a to the epsilon. OK. So there are a bunch of variations. So there's a whole circle of theorems that cover many different shapes, the small neighborhoods of various different manifolds. So for example, they did in any number of dimensions the paraboloid, or the cone, or the sphere, or the moment curve, which is a generalization of the parabola in a different way. I remind you, the moment curve is the curve parametrized by t goes to t squared, t cubed, up to t to the n. This one is joint with me. And these are Jean and Ciprian. And there's more stuff, too. I won't put them all. But for a wide variety of shapes and a wide variety of ways of cutting them up, this school of thought has figured out how to estimate these things. OK. So the first lecture, the goal of the first lecture is to introduce decoupling, to get used to it. So we're going to look at some examples. We're going to give an application. And then we're going to start to talk a little bit about the proof. So I'd like to start getting a feel for this theorem by looking at some examples of different functions f and seeing how this plays out. OK. So example. Yeah, thanks. Y6? Yeah, that's a great question. That's a great question. So we're going to see Y6 in the examples, and I think that's the best way for me to answer it. Yeah.
And all your variations are kind of quadratic?
Quadratic, in the sense that we always do this?
Well, that, the curvature is always, in paraboloid, it's here, it's second order.
Yeah, right. Yeah, so you could ask what would happen if we looked at the curve t goes to t comma t cubed, something like this. Yeah, and so this is also understood, and there's a part near 0 which is extra flat, and then there's a part far from 0 which is curved and looks more like a parabola. And there are some special considerations in the part that's close to 0. Yeah. It would be neat. One dreams of a sort of universal decoupling theory that would, instead of having 12 theorems that describes what happens for 12 different shapes, there would be one theorem that would say for every shape what is the decoupling constant. And we don't. That's not yet available. But if you read the 12 theorems, you start to feel like you have a decent sense of what's going on. OK. Other questions before we keep going?
Is there anything that's known about if you replace the p on the inside of the norm with the p on the outside? So if you look at the square function?
So if I look at, sorry, go ahead.
So what happens if you form the square function and look at the square function at all? Is there anything known about that?
So talk about the sum of f theta squared to the 1/2 LP. Is this your question?
Yeah.
Yeah. Okay. Cool. So a bunch of things are known about this, but it's harder than that. I'm not really answer your question, but maybe I'll explain what the question was about for everybody. So where did this thing come from? One way to think of it is as being a kind of a pseudo-random condition. So as a model to keep in mind, So as a model to keep in mind, what would happen if the f sub thetas were independent random variables? Independent random variables, which they're certainly not, because it's very difficult for many different smooth functions on r to the n to be independent. But we can think of this. I'll argue that we can think of this as a kind of quasi-independence condition. So what would happen if they were independent random variables? Then and f is their sum. So then we would have f theta of x would typically be around this sum of the squares, sum of f theta squared to the 1/2 with high probability. And that would imply that the LP norms of these things would be similar to each other. Sorry, there's no theta there. So that would imply that FLP was around the LP norm of this thing for reasonable p. OK. Cool. And this is actually stronger than what happens there. It's an exercise with Minkowski's inequality and stuff like that to see that that in turn implies that the LP norm is smaller than the square root of the sum of the squares of the LP norms. So this quasi-randomness is stronger than implies a decoupling inequality for all the different p's. OK. And this square function thing is the thing that people have been thinking about for years and years. And there are some very hard problems. So for example, it's an open problem to understand the sphere, this square function for the paraboloid or the sphere, or I think the cone. Those are hard open problems. And what we're going to be talking about that is a weaker form of this quasi-randomness. So we're going to talk about the younger sibling of this old quasi-random inequality. But I'm going to argue that this kid sibling has some very nice properties that allows us to study it better and to understand it better than we understand the square function thing. OK. And we'll get to that in the last part of the talk. We're going to talk about what is very special about writing the inequality in this way, which makes it accessible to study and makes it, I think, important. OK. Let's start to look at, yep. All right, what about this? Yeah. Yeah. OK, so this is going to be, right. This is going to be not exactly, yeah. OK, so two examples to keep in mind. So as a warm-up to the examples that I had planned, one thing that could happen is that the supports of the f theta could be disjoint from each other. If that happens, then the LP norm of f is exactly the sum of the LP norms of f theta to the p to the 1 over p. Maybe I should mention that I will always be interested in p that are bigger than 2 in this talk, which is true in that theorem. So in this case, the LP norm of f is very nicely controlled. It's smaller than the right-hand side in the decoupling theorem. And from the point of view of your reverse inequality, now it's bigger. This is the worst. This is the way to make the LP norm of f the smallest, to make it disjoint. OK. The opposite of this scenario is that the supports of f theta are all the same. So the opposite of that is that the support of f theta are all the same. And in fact, let me say that the norm of f theta is essentially the characteristic function of one set E for all the different thetas. That's the opposite of having disjoint support. And then the best you could hope for is that the norm of f is around a to the 1/2 on E, around square root cancellation, where a, remember, is the number of different thetas. This is the best you could hope for. And in this case, you would see that all of the LP norms of f go like the sum, go like the right-hand side. Yeah. OK. So if a way of understanding, yeah. So this theorem says that we get square root cancellation when we add up the different f thetas, not at every point, but in a sort of an LP sense. And so we should be able to say in a situation like this that at most points there's a square root cancellation when we add up the f thetas. Cool. OK. I'd like to show you some other examples, though, that are connected to the specific geometry of this parabola, and which explain, for example, where this p goes between 2 and 6 comes from. OK. So let me do the following thing. Let me take a smooth bump. So eta theta is a smooth bump supported on theta. And I'm going to normalize it so that its integral is 1. And then f theta could be the inverse Fourier transform of this thing. And so let me describe to you what f theta is like. So if theta is a small rectangle like this, where this direction is 1 over a, and that direction is 1 over a squared, then its inverse Fourier transform will be essentially supported on the dual rectangle. So the dual rectangle is called theta star. And with respect to the same axes, it has a long direction, which is the reciprocal of that short direction, and a shorter direction, which is the reciprocal of that. And the size of f theta is approximately the characteristic function of this dual rectangle. So I don't want to write too many calculations on the board. It's not hard to check this at home, but let me describe how you might do it. We all know that if we just took a smooth bump function on a unit ball, and we took its inverse Fourier transform, we would get kind of a smooth function on a unit ball that rapidly decaying outside. And this scenario is the same, except instead of the unit ball, we have this rectangle. And you can get between a square and a rectangle by making a linear change of variables. So if you do that linear change of variables and unwind it, you'll see that f theta essentially lives on a shape like this. OK. Now f theta is also oscillating. And if we pick one point, let's call this omega sub theta, one point in the rectangle theta, we would expect that f theta looks like it's oscillating at about this frequency, omega theta. So without being super rigorous, I'll say that f theta of x looks a lot like e to the 2 pi I omega theta dot x times the characteristic function of the dual rectangle. Okay. So that's one building block, my f theta. And to make f, I'm going to add up the f theta for all of the different thetas. F is the sum on theta of f theta. I like to make a picture like this. So I have all of these different rectangles. So each of these rectangles is a theta star for a different theta. And because you can see the direction of theta is changing as I move around the parabola, therefore the direction that these rectangles are pointing is changing. Okay. Yeah. Now, each of these f thetas is oscillating, but at the point 0, each of them is 1. So at the point 0, they just add up constructively. So f of 0 is a. And in fact, if we think about it a little more, we'll see that the size of f of x is around a on the unit ball. Because if we're on the unit ball, or maybe a ball of radius a half, this phase is approximately positive. So all of the phases are approximately positive, and they add up constructively. So I'm going to symbolize that by drawing a red dot at the origin. And that red dot is the unit ball. OK, so the way that f looks is, roughly speaking, that it's quite tall at the origin, where we have constructive interference. All of the f thetas are positive. And then it gets smaller as we move away. Out in this region, there's only one f theta, and it has size 1. And for large p, this red dot actually dominates the LP norm of f. So FLP is actually around a for p bigger than 4. You can think of that as an exercise. What's clear from our discussion is that the LP norm of f is bigger than a for all p. And this is the dominant term when p is big enough. OK. And the LP norm of f theta is easy to understand. The LP norm of f theta, so f theta has height 1, and it's supported on this region theta star. So that's the volume of theta star to the 1 over p. Theta star is a rectangle with those dimensions, so it's a to the 3 over p. OK. So let's do a quick calculation now about what this says about the decoupling constant. And we'll see that this theorem could only possibly hold when p goes between 2 and 6. So if we had that dp of a grew like a to the epsilon, then we would have a, the LP norm of f, would be bounded by a to the epsilon, the decoupling constant, times an a to the 1/2, because we have a terms, and we have a square root cancellation, times the size of each term. We have this, and that tells us that p would have to be at most 6. OK. So I don't have a more conceptual explanation of why p goes at most 6, but by checking a simple example, we can see that that's the right range. And actually, when we talk later about the proof, the way that I like to think of the proof of the decoupling theorem is that it shows that the general theorem can be reduced to a small number of special cases. And then you check those special cases, and whatever happens, happens. OK, let me erase this, because it's not that interesting, and show you some more examples. So that was one example where the decoupling theorem is sharp. But something that I think is interesting is that there are quite a lot of examples where the decoupling theorem is sharp, and which perhaps makes it a hard thing to prove. So let me show you another one. So more examples. So let's go back to f theta. The first thing I did is I took a smooth bump function on theta, and I took its inverse Fourier transform. I could also take a translation of that. I could take f theta to be, so f theta of x to be eta theta inverse Fourier transform of x minus v for some vector v. And translating things in physical space doesn't change where their Fourier transform is supported, so that would still be admissible. And I could take a linear combination. So more generally, I could say that f theta of x is a sum over some j's of some constants times eta theta inverse Fourier transform of x minus vj. And geometrically, that would look like the following. I have here my theta, and then f theta would be a sum of translates of the first example that we had. Not necessarily evenly spaced, but anyway. This thing is called a wave packet decomposition. So each one of these is called a wave packet. OK, so that leads to some more examples. So my second example is just to take a whole bunch of disjoint copies of my first example. So example 2, G is equal to n disjoint copies of example 1. So geometrically, it looks like this. And so on. And there's a red dot in the center of each of these where there's pure constructive interference. OK, so for a given theta, the LP norm of g theta is n to the 1 over p times the LP norm of f theta, because instead of having one wave packet, I have n disjoint wave packets. And the same applies to the LP norm of g. The LP norm of g is n to the 1 over p times the LP norm of f, because I have n disjoint copies of the function f. And these have multiplied the same way. And so maybe I should let me keep up the definition of dp. Let me just keep this handy. So when I replace f by g, both the left-hand side and the right-hand side get scaled by this factor n to the 1 over p. And the examples are still as sharp as before. OK. Cool. And now let me show you an interesting example, an example where it won't be easy for us to evaluate by hand what's happening, but where the decoupling theorem, which shows how the decoupling theorem says something interesting, shows the kind of thing that it tells us. So what I'd like to do is to bring the wave packets in example 2 closer together so that they interact with each other more. So there'll still be, for each theta, there'll still be n separate wave packets. But there'll be a lot of different interactions between those wave packets, which will be very hard to control by hand. So here's my eraser. So example 3. So for each theta, h theta will consist of capital A wave packets in the ball of size a squared. So I'll draw it over here. So the ball of size a squared. And for a given theta, we cover this ball with wave packets that are shoulder to shoulder with each other. And I think to keep the picture from getting too muddied, I'm only going to draw one theta. But there are all of these different directions theta. And in each direction, I want you to imagine that there's a row of parallel rectangles that are covering this ball. Cool. In equations, we have h theta is a sum. J goes from 1 to a of wave packets, Cj theta complex number times eta theta check x minus Vj. And so I'd like you to imagine that these Cj theta are all unit complex numbers, but we can adjust the unit complex numbers, which adjusts the phase of the wave packet. So there are a squared different numbers here that we can adjust. Okay. So it's easy to figure out the norms of h theta. So h theta L6. Well, the norm of h theta is basically the characteristic function of this ball. So this is a to the 2/3, 4/6 or 2/3. And so decoupling tells us that the L6 norm of h is bounded by a to the 1/2 plus 2/3 plus epsilon, so a to the 7/6 plus epsilon. And I want to think about what this is telling us about how the different functions h theta are adding up. So let me say that C is defined to be the set of x so that h of x is comparable to A. And this L6 norm gives us an upper bound for the volume of C. The upper bound is that the size of C is basically bounded by A to the 1 plus epsilon. Okay. Now, it's possible for this C to have size A. I'm going to show you how. And in fact, there are lots and lots of ways for C to have size A. And therefore, it's, I think, remarkable that C can never be really bigger than A. So let me explain how to arrange that C has size A. So suppose that S is a set of A unit balls, and that they're fairly spread out in this big ball. So they're all contained in the big ball. And they're fairly spread out in the sense that if I take one of the wave packets and I intersect it with S, then I only get on the order of one ball. So for example, I could take evenly spaced red points going horizontally across. Or I could take A random red points, and similarly, a typical wave packet would only hit around one of them. Okay. So whenever I do this, I can now choose the coefficients, Cj theta, these phases. I can choose them so that the sum is around A on S. So the way I do that is I pick a red point, and I want to arrange that H is really big there. I look at all of the wave packets that go through that red point, and I tune the coefficients of those wave packets so that they all align. They're all, say, all positive at that point. And because of this condition, a typical wave packet, so I can only choose each coefficient once, but a typical wave packet is only going through one red point, so I only have to choose it once. Okay, so there are lots and lots of ways to arrange that at a set of size A, I get this constructive interference. And the theorem says that there's no way to arrange that to have that much constructive interference on a really bigger set. That's the worst that can happen. In other words, if there's a sort of bad coincidence at these points, at each of these points I get a lot of positive terms adding up so that the sum is big, then it can't also happen at other points at other places. Cool. Okay, so that's the kind of thing that decoupling is telling us. And that finishes my circle of examples. Okay, so now we have hopefully some sense of what the theorem is saying. And now I wanted to show you an application in order to justify, in order to maybe convince you that the theorem is important, or to, I don't know, show you what it's good for. Yeah. So there are a number of applications, but I picked out one to show you, which is an application in number theory, which to me seems the most striking, because number theory doesn't sound immediately connected to the question that we're talking about. Okay. Cool. So the application I want to show is about exponential sums. And there's a general connection between exponential sums and decoupling. So it says the following thing. So if I have a decomposition, omega is a disjoint union of some thetas. And for each theta, I pick a point, omega theta, which is a point in theta, but it's also an integer point. So I'll be interested in exponential sums where the frequencies are integers. OK, and then I look at this exponential sum. I sum over theta with some constant e to the 2 pi I omega theta x. Let's call this g. And the proposition says that the LP norm of g on the unit cube is bounded by the decoupling constant of this decomposition times the sum of the squares of the coefficients to the 1/2. So bound for an LP norm of an exponential sum. OK. So this is fairly easy thing. Let me first make the following point. Let's write this as g is the sum of g theta. And this norm of c theta is the same as g theta LP of the cube. So this looks like I just plugged in the definition of decoupling, that the LP norm of the sum g is bounded by the sum of the LP norms of the pieces, g theta, squared to the 1/2. It looks like I just did the definition of decoupling, except I cheated a little bit because I don't have Rn here. I have the unit cube. And in the definition of decoupling, apparently I didn't emphasize this point, but what this little p means is LP of Rn. OK. So why is it OK to put the unit cube instead of all of Rn? Well, it's OK morally because all of these functions are periodic. So the way they behave on a large ball or on all of Rn is just determined by how they behave on the unit cube. So let me give you a bit more of a sketch. Let me sketch the proof of this. So I choose some large number r, so that if I take the ball around any of these frequencies of size 1 over r, it's contained in the region theta. Actually, let me add a hypothesis here, that these theta are open sets, so that I can do this. OK, and then I take a function eta, so that the support of eta hat is contained in a ball of radius 1 over r. And then the function eta, it looks like, so eta is around 1 on the ball of radius r, and then it's rapidly decaying. OK, so my function f theta will be eta times g theta. G theta was just a complex exponential at frequency omega theta. So this guy is going to have Fourier support in the ball of radius 1 over r around omega theta, so it's OK. And f is eta times g. And so now I can apply my decoupling to f and f theta. And the point is that everything behaves proportionally to how it behaved for g and g theta. So by periodicity, f theta LP is like r to the n over p times c theta. And FLP is like r to the n over p times GLP. And I just plug in the definition of decoupling about how these things relate, cancel these factors, and we get this inequality. OK. OK, so an interesting example is, so the parabola is a sort of interesting example for applying this. But a more interesting example for applying this proposition is the moment curve. So we have the moment curve in Rn. So here we have the origin. Up here we have capital A squared, capital A to the n. And then we have capital A integer points going along here. And to make a decoupling theorem, we want to cover the moment curve by some regions, one lattice point per region. Those are my thetas. OK. And so the decoupling theorem for the moment curves tells us that dp of A is small, like A to the epsilon, for p up to n times n plus 1. So for a reality check, a sanity check, when n equals 2, the moment curve is just the parabola that we've been talking about, and this number is 6. And then this is how it grows when we increase that. OK. So we can use this theorem and this little proposition to estimate some exponential sums. Here's an exponential sum of interest. It's just the OK, so corollary, we take the exponential sum e in ln n plus 1 of the cube. This is smaller than a to the n plus 1. Sorry, a to the 1/2 plus epsilon. OK, and this is sharp up to the epsilon, and it was conjectured by Vinogradov back in the 40s or 50s in connection with number theory. So let me tell you what is the connection to number theory. Well, OK, so there are a lot of connections to number theory. The one that's closest to the surface, although not the one which is most important, is that this norm actually encodes the number of solutions to a certain Diophantine equation. So connection to number theory. That's right, that 2s is this n times n plus 1. And the thing that we know how to estimate is the integral of the norm of e to the 2s, which is the integral of e to the s times e bar to the s. OK, and so now what we're going to do is we plug in the definition of e and e bar, and we expand this thing out. We're going to get a bit of a mess, but we're going to get a sum of terms which is each the integral over the cube. So when we expand this out, we'll get a bunch of terms that are each the integral over the cube of e to the some vector times x, some integer vector times x. And when that integer is 0, it counts as 1. When the integer is non-zero, it integrates to 0. So it's going to tell us the number of times that exponent is 0. OK, so I'm going to do it as create a bit of chalk. So this is the integral of the sum. I'll have s terms from expanding out this e. I'll call those a1 up to as. It's from plugging a different name for this variable a in each of these factors. And then I'll have some from the bars. I'll call those b1 up to bs. They also go from 0 to a. And then the thing I'm summing, let's just think about the coefficient of x1. So I get an a1x1 plus asx1 from these guys. And then I have minus signs because of the complex conjugation for the b's. And then there's stuff with x2 and so on. But let me pause while writing this horrible long equation. Did this make sense so far? OK. So then if we do the same thing with x2, we'll have a1 squared plus as squared minus b1 squared minus bs squared x2, and so on up to xn. OK. We take this sum out of the integral. We have a sum of a whole bunch of terms. And as I was saying before, if each of these numbers is 0, then we get a contribution of 1. And if any of these numbers is not 0, then we get a contribution of nothing. So therefore, this is equal to the number of solutions of the following Diophantine system. The aj's and bj's go between 0 and capital A, and they're integers. And they obey the equation a1 to the j plus as to the j equals b1 to the j plus bs to the j for the j's from 1 up to n. So this integral that we estimated with Fourier analysis is telling us how many integer solutions there are to these Diophantine equations. And if you unwind what the estimate is, corollary is that the number of solutions to this is bounded by a to the s plus epsilon. And this is also sharp up to the epsilon. So I don't know if this is that interesting, but it's easy to see that there are at least a to the s of these solutions, because we can always choose a1 equals b1, as equals bs, and so on. So those are called trivial solutions. And the number of trivial solutions is just the number of choices of a1 up to as, which is already a to the s. Less obviously, the number of non-trivial solutions is also on the order of a to the s. And the content of the corollary is that it's not much bigger than that. OK. So I think that this is kind of a striking thing. This is a number theory problem. It's not obvious from my presentation that this is a particularly important number theory problem, but it actually is important. And since Vinogradov, many people have tried to estimate this. And so n equals 2 is not that hard, and was done sort of classically. And n equals 3 was done just a few years ago by Trevor Woolley. And the higher values of n have so far can only be done via this Fourier analysis argument. So I think it's evidence that this decoupling thing should sound difficult, that it can prove something in another field in number theory, which even is pretty hard to prove in a purely number theoretic way. Yeah.
It looks like you don't need this integer requirement as long as your coefficients are sort of spaced. Like with this exponential sum, you're never using anything arithmetic about.
Yeah. OK, so the question is, do we really need these to be integers?
Yeah.
And where did we use it in the proof? The place that we used it in the proof is that is periodicity.
Oh, okay.
Yeah. Yeah. Thanks. Yeah.
P has to be less than 6, right, in the origin of the, and that corresponds to n equals 2?
Yeah, so in the original theorem for the parabola, p goes up to 6, and that corresponds to n equals 2. If n is 2, this is 6.
But for moment term, you prove decoupling for every n, for every p, sorry.
So for the moment curve, p can go all the way up. So for the n-dimensional moment curve, so the curve depends on n, p can go up to n times n plus 1. So Vinogradov, it wasn't only focused on knowing how many solutions there are to this equation. What Vinogradov, I think, really cared about is he wanted to study this thing E, and he wanted to understand how big is E of x for various values of x. And that's a very hard problem. It remains an open problem. I mean, there are some bounds, but it remains an open. The bounds are much bigger than the truth, probably. And he had a neat idea how you could bound the value of E at particular points if you knew an LP estimate for E. And he was motivated by that to prove these LP estimates. And for anyone who's interested, there's an analytic number theory program going on here where people know a lot more about that than I do. OK. So how are we doing on time? OK. So there are more yeah.
So why Vinogradov didn't ask the question when n is fixed and number of is not n plus 1 or some other?
OK, yeah. Yeah, so Vinogradov wanted to know about the LP norms of E for every E, for every P, for every P. Yeah, and I didn't write them all down, but this is the hardest one. And this same machinery, we now know the LP norms of E for every E. And the way it goes is that the L infinity norm of E is easy to understand. And by interpolation between this and the L infinity norm, that gives all of the exponents bigger than this. The L2 norm is also easy to understand. And interpolation between this and L2 gives all the exponents small. Yeah, other questions?
Is that interpolation expected to be wasteful below n over n plus 1?
Yeah, yeah. We brought up what are the LP norms of this sum, and I said you can interpolate. Well, let me see if I'm answering your question. So at the origin, this thing has size A, and there's a little region around the origin where it has size A, where this phase hasn't changed very much, and that little region accounts for this norm, for all p bigger than or equal to n times n plus 1. And then on the other hand, the L2 norm is easy to understand, and at a typical point, the size of E of x is close to a to the 1/2, and that accounts for the L2 norm. And I think the question is, if you look at heights in between this maximum height and this typical height, and you ask how big is the set of x's where E has that height, do you get that size just by interpolating, or is it wasteful? Is it smaller? Is that the question?
Yeah, so for instance, at L4, you say better than that epsilon loss. Like that's what I'm wondering. Because it doesn't look like there's going to be much of a loss at L2. At L infinity, you know exactly what it is. But I just sort of wonder if you get closer to 2.
This is fun. OK, I repeat the question one more time, but then maybe I'll move on. So at p equals 2, this thing is a to the 1/2 with no epsilon, trivially. And if we interpolate, then for all the p in between 2 and n times n plus 1, we can interpolate, but we have this epsilon. And the question is the epsilon real? Could we get rid of that epsilon maybe in the in-between places? Yeah. I don't know that. I don't know how to do it. I don't know that. I think it's an open problem. OK. I wanted to start to talk a little bit about the proof. So there are more applications of decoupling. But my feeling is that some of the applications are just one line. And in general, the applications are not that hard to read. But the proof is kind of hard. The ingredients of the proof are elementary, but the proof is kind of hard. And for me, it took a long time to digest. So I want to focus on the proof and start to put in some ideas out about what's involved. And then we'll talk, the next 2 lectures are all about the proof. Yeah. So I said that the ingredients of the proof are pretty simple. Let me write down what the ingredients. So the proof uses orthogonality. It uses some simple geometry that we'll talk about later. And it uses looking at the problem at many scales. And I'm going to put an exclamation point there. That these things were around. And what I think is the really new thing in the proof, the fundamental new thing, is a way to leverage looking at the problem at lots of different scales. You know? Maybe it'll take some time to explain how they do that, but let me just give an indication that they're looking at the problem at many scales. We can say the theorem in a slightly different way. So theorem prime. So the way I said it before is that dp of a is bounded by some constant times a to the epsilon. But equivalently, we could say it's actually bounded by a to the epsilon if a is big enough. So if a is bigger than some a naught that depends on epsilon. And it's an interesting exercise to go through the proof and figure out what is a naught of epsilon. I had a talk with lunch with a graduate student who's doing that very carefully. He's going to write detailed and correct things. But anyway, my sense of it is that the proof gives a naught of epsilon is something like e to the 1 over epsilon. Or worse than this. The truth is complicated, but it's something like this. So well, you all can do this, but for example, if epsilon is 1/10, we need a to be bigger than probably 10 to the 1,000, maybe 10 to the 10,000, something like that. Something that I'm tempted to call astronomical, but I have relatives who are actual astronomers, and there are no numbers that big in astronomy. OK, that's probably not the truth. The truth is more like e to the 1 over epsilon, which is still a little bit big. But the reason that this number is so big is it means that we have a huge number of different scales to look at the problem with. And the really cool new idea is a way to make use of all of those different scales to do something cool. OK, now another thing I wanted to say is that, so Ben asked earlier about square functions. There is this classical way of thinking about how the f thetas were adding up, which is called the square function estimate. And then there's this new way, the decoupling way. The decoupling way is only asked in the 1990s. It was asked by Tom Wolfe, and to the best of my knowledge, for the first time in the mid-1990s. It's a pretty simple looking, I've erased it again. But anyway, it's a pretty simple looking thing to ask about. For the idea of Fourier analysis is we take a function and we break it up into different pieces according to their frequency. And then we have to recombine them. And we want to understand how the size of the final function is related to the size of the pieces. It's a fairly simple thing to write down, but that no one had done before. And the particular structure is very important. It was very clever to ask the question in this way. And what's clever about it is that it goes along with this many scales idea. OK, so I think we should stop there. So at the start of lecture 2, I'll explain how the particular form of the decoupling inequality is good for looking at many scales. Thank you. Yeah, let's see if this is still up there. So the question is, if we crossed out some of these equations, say the equation for j equals 2, then we would, of course, have more solutions. And the question is, what could we say about the number of solutions with these methods? Yeah. OK, so the methods can say, I don't know, the methods can say something about it, but I don't know what off the top of my head. Geometrically, if we forget about equation number 2, it means like we would have this moment curve, but we forget about this coordinate. So now we have a new curve, the curve that's t goes to t comma t cubed t to the 4th, et cetera. And we have to work with the geometry of that curve instead of the geometry of the moment curve and use the methods, and probably something will result. Yeah. What's that?
It's a surface. One variable is free.
I guess we could think of it as a surface by keeping that second variable and letting it take any value. But since it's not doing anything, we could also just never talk about that variable. And then we'd have a curve in n-1 dimensions. Yeah. Surfaces also come up naturally if, let's see, if we had, instead of a sum over one variable, we had a sum over two variables, and we had different powers of the two variables. That would give us a surface instead of a curve. And so all of the different, I wrote down a bunch of different geometric objects. All of them come up in different reasonably natural problems in number 3. Yeah?
Are there any conjectures about the true value of the decoupling constant in these situations?
In which situations?
So, for example, in the parabola, you have a to the epsilon. Is it log a? Is it what's the?
OK, yeah. Yeah, it would be very interesting to do that better. So the conjectures are the optimistic conjectures. This is still on the board, which is nice. OK, so on the other end, we know that d6 of a is at least log a. And for 2 less than or equal to p less than 6, there is no interesting lower bound. But I can say that we know that this is at least 1. Which is not completely trivial. OK, so then I think it's reasonable to conjecture that this is the truth. I think that, yeah, that's what I would guess.